40 from last time, so this is sections 40.5 and 40.6. And building off of last time, what we conceptually began to understand about population dynamics, about the picture I showed you, births plus or rather births minus deaths, and immigration minus emigration go into population size. So we looked at that conceptually last time, how if you take the number of births in a population, subtract the deaths, add to it the number of emigrations minus the number of emigrations moving out, you get the population size, and that's population dynamics. So that's how a population changes, or it's over time in its size. We're going to look more at the math that goes with that today. So on the back of your formula sheet, this is what we're going to be talking about. So what we talked about before was this notion of population size, and N is going to be the population size. So we talked before that births and deaths are the two main factors that influence population dynamics. So one assumption is that we're going to make right now for this modeling, for mathematical modeling, is that emigration and immigration don't significantly contribute to or significantly increase or reduce our population size. In real life, that's not true at all, but we can get this sort of sense with our model. So we can take this simple equation, our population size equals our births minus our deaths. However many are born in a year minus however many die in a year, that is going to be next year's population size. Or that's going to be the amount of increase, all right? So we can say that the change in N for a specific period of time, for some time period, and that's what this side of the equation is saying. Change in our population size over a specific amount of time is going to equal our births minus deaths. That makes sense, right? How our population changes if we can only manipulate people that are born or people that die. The change in our population over a certain period of time, a year, let's say, is going to equal however many people are born in that year minus however many people that die. Good so far? All right. We can go from there and introduce a per capita birth rate. So we use a little b to represent that. So little b means how many individuals are born for every individual in that population. So if we have a population of 100, all right, and let's say 20 babies are born, we could say per individual, so per one individual organism, 0.2 are born. 100 divided by 20, 0.2 individuals are born for every organism that exists in that population. So if we want to get the per capita birth rate is little b, we can multiply that by our population size to get how many births we could expect in a year. So for example, if we know b equals, let's say from our example, 0.2 babies per person, then we can expect in 1 year, n is 1 year, that we'll have b times n, we'll have 0.2 babies per year times how many people in that population? 100 people. And that equals, we can expect about 20 babies. Alright? We can do the same thing with how many people we expect to die. The per capita death rate, which we call M for mortality, we can find the expected number of deaths the same way. I'm not going to rewrite it, but the same way. If M is the mortality, the percentage of the population that dies every year multiplied by the population, that's how many times we can expect an individual, or how many individuals to die that year. So putting it all together, we can find the expected per capita, what's called the per capita population change with this equation right here. And this means, how do we expect, how many individuals do we expect the population to increase or decrease by, given the current population size? So all we're doing is saying that we are going to take per capita birth rate, subtract the per capita death rate or mortality rate, and get the expected population size right there. Alright? So, what did I do? This is essentially the same equation as this right here. 1 and 2 are essentially the same, except this is in terms of per capita. Per capita. So this can be like our expected. If we know B and little m, we can calculate what we'd expect over a period of time our population would increase and decrease by. This is important population modeling. Right. We can also change this formula to represent how the population is changing on average per individual. So the per capita rate of increase is what we're going to say is R. So R is going to represent our per capita birth rate minus our per capita death rate. So if R is positive, that means on average we can expect the population to grow. If R is negative, we expect the population to shrink. R is 0, stays the same. I think this, which I'll label equation 3, makes a lot of sense. Right? The rate of increase or decrease equals the rate of births minus the rate of deaths. Perfectly, I think we're okay with that. So in population size, in terms of per capita growth rate, we get equation 4. And I need to show you that this is the same as 2, which was that. Per capita birth rate times n minus per capita death rate minus n. So what happens is, if R equals B minus M, what I'm going to do is I am going to factor out an n from this side. Now, by definition, R equals B minus M. B minus M right here, I'm going to substitute R for B minus M, and we get this equation number 4 right here. So, please realize I just used a new definition of B minus M for rate of per capita increase, and I just rewrote equation number 2 from this slide in a different way, and it looks like equation number 4 right there. So this is equal to that. Alright? Hopefully you can see that point. Now if we use calculus, we can determine this population size instantaneously. Okay? Instantaneously. And the way that we do that is saying that at any point in time, so any infinitesimally small point in time, our rate, our per capita growth rate is going to be our instantaneous, instantaneous meaning at that moment, per capita growth rate times n. All right, and we use this in ecology all the time. There's a lot of calculus in ecology. We use this in ecology all the time because it's the basis of all of our population models that I'm going to show you next. So this is important, equation 5. These equations are on the back of your sheet. You won't need to remember how I derived them, but you should remember intuitively that they make sense, what they mean, and how they make sense based on the factors of births and deaths, increasing and decreasing the population. All right, so the first thing we come across is exponential growth, and that is based on equation 5, dn dt equals instant r times n. In an ideal population, so we're starting with an ideal population. This isn't just any population, it's an ideal one. With infinite food, water, shelter, resources, and etc., the population will grow at a maximum rate. Can't grow any faster. Matings are happening and births happening as fast as possible. And that rate is called R max. All right? R max is the maximum possible rate of growth. So this population, a population that grows according to R max, will have a population increase according to this equation, where dn dt is equal to R max n. That is just like equation 5, except instead of R insta, we are replacing that with R max. Because R insta is at R max, okay? It's the maximum up it can go. And we get an exponential curve. It's also called a J curve, because it looks kind of like the letter J. All right? So here we can see, for different R maxes, we can see how a population grows very slowly at first, but then exponentially, that makes sense, right? Exponentially quicker as time goes on. So this huge upshoot, the more time that goes on, the faster the population is growing. This is the exponential growth model. And this is the equation you will see on your AP Bio formula sheet. Exponential growth. Some organisms grow according to exponential growth, like bacteria, microbes, and rapidly growing populations at the beginning of their growth. So newly emerging populations will grow according to exponential growth to start out with, not indefinitely. Nothing really grows exponentially forever. However, the sad part of it is resources in space are not unlimited. That's one of the assumptions we made with this exponential growth model. They're not unlimited. There's a finite amount of organisms a given area can support before space or resources or mates run out. This is the definition of carrying capacity, or K. We represent it with a capital letter K. Carrying capacity is the number of a given type individuals of a given species a given space of an environment can hold. So this carrying capacity changes over time, changes between environments, and is different for different species even in the same environment. One environment can hold more lions than bats, or one more lions than grasshoppers. Crowding, resource limitations, and diseases profoundly affect the rate, R, of population growth. And so, in normal populations, one thing is usually true. R decreases as N approaches K. This makes sense, right? The population will grow less rapidly as the number of individuals that are in that population approach the maximum number of individuals in that population that environment can support. That's just using some deductive reasoning, okay? All right, that's the basis of our modeling our carrying capacity. So we can model population size with carrying capacity in mind with the logistic growth model. So the logistic growth model takes carrying capacity into account. In this model, like we said from our observation over here, we changed basically, we started out with an exponential growth model of dn dt equals r n. We changed it to take into account this factor right here, that r decreases and n moves towards k. And we get, I'll call it equation 6, dn dt equals r max times n, all of this multiplied by k minus n divided by k. So, conceptually, what does that mean? This is our exponential growth model, r max divided by n. So, when n is 0 or very small, we're just starting out, this product will be very close to r max times n, very close to exponential growth. So when the population is small, it will increase like an exponential growth curve. You can see that by the overlap of the red and the blue in this graph. However, as n gets proportionally closer to k, this numerator gets closer and closer and closer to k minus k, which would be 0. But this is going to get smaller and smaller and smaller and smaller on the top. So when we divide it, this will get smaller and smaller and smaller, and so what we multiply, our whole product, will get smaller as n approaches k. So the growth will decrease just like we wanted it to do. So k minus n represents the fraction of or the number of individuals that the environment can still hold, and k minus n divided by k represents the fraction of the number of individuals the environment can still support as a fraction of its total possible capacity. Okay? So, for example, the maximum rate of increase for this population size. So at 25, the max rate is always going to be 1 for this population. As we gain more individuals, this numerator, this number right here is going to get smaller and smaller and smaller and smaller as the numerator gets closer and closer and closer and closer to 1. 1 divided by the same number is getting closer and closer and closer to 0, and this number is going to get smaller and smaller. So our R max, our R max n value is going to get bigger and bigger, until we get to a point where it's 0. So when we get to our 0 point, that is when we can't support any more individuals. So our growth rate is going to get smaller and smaller and smaller and smaller until we hit 0. And when we hit 0, that is when n equals k. This part in parentheses equals 0, and our growth is 0. When our growth is 0, that means we've hit carrying capacity. So carrying capacity is this line on the graph, and it represents the point at which we no longer can support any more organisms. The population graph of a model of a real population doesn't look like exponential, but it also doesn't look like just a growth model. Why is that? That is because let's go back. Some small animals and some microorganisms do exhibit logistic growth. They're in a very confined, controlled, constant environment, but real environments change. They're predators, interspecific, intraspecific competition, different natural disasters or situations or droughts or famines or things. It will never look like this perfect S-curve like that. It'll never look like that. All right? Instead, it's going to look more like this. Real populations don't smoothly approach K. They might shoot up, and usually they'll surpass K. And they'll oscillate around K, and sometimes, growing, shrinking, and sometimes they'll even do things like this. They're never going to be a nice S-shaped curve. However, we're talking about rough modeling, just so we can get the general idea, and in most cases, rough modeling, this oscillatory model, which is this, is a good intermediate between this jagged realistic model and the logistic growth model. The last part of this has to do with ways in populations can change and the restrictions. So population size can be affected by biotic and abiotic factors. And we also group those factors on how they influence a population size, whether they depend, whether they are affected by the density of a population or not. So density-dependent biotic and abiotic factors limit a population size only after the population has reached a critical density. So for example, food and water and shelter and infectious diseases, they are all more devastating, or they have a profound effect only if the population is a certain size. If the population size isn't big enough, having less food won't really make a difference because there was more food than they needed in the first place. If there's not a big enough population for an infectious disease to spread, it won't cause noticeable mortality. However, there's other things called density-independent factors that no matter the population size, it's going to have an effect. And floods, storms, wildfires, they kill off animals, regardless if very densely populated, less densely populated. Huge tsunami wipes out North America, lots of death. Doesn't matter that population density Wyoming or New York. Sure, it will be different amounts, but it still has the same noticeable effect. So these factors, biotic and abiotic, can be density dependent or density independent. Also, things that are density dependent or density independent are these trade-offs in population growth. So another thing that affects population growth is the fact that no organism can produce and provide for unlimited amounts of offspring in an environment. There's a trade-off, we say, between the quantity of offspring an organism can have and the survival, the amount that are survived. So some organisms produce many small offspring at once with very little energy, very little care and investment, like birds, like fish, like a lot of trees, pollinated trees, and we call these R-selected species. R-selection. And other species have very few young, right? They're larger on average, but they take a lot of parental care of them. They invest a lot of nutrients, a lot of energy, and we call these this a K-selected strategy. In one case, selection for traits that are beneficial at high population densities are known as K-selection species, or density dependent. So this strategy pays off when there is population near carrying capacity. On the other end, R-selected species are very good, or are very good trend for traits that maximize reproduction success at low densities, very, very far away population size from carrying capacity, or density independent. Some other characteristics of both types are R-selection is small. Organism sizes are small. Energy they invest in each individual is low. They have a lot of offspring. Early maturity, so they can reproduce fast. A short lifespan. Usually reproduce once, and they have a type 3 survivorship curve. So it looks like this, like exponential decay model for our R-selected species. K-selected are basically the opposite. They're like humans. They're a survivorship curve 1 or possibly 2. That's our K-selected species. And birth and death rates can also be density dependent or density independent. They change. They're affected by their environment. All right, so there are trade-offs, and these different strategies have evolved in relationship to our models with R and K selection to help organisms survive in the environment in different situations, close to and far away from carrying capacity. That'll be it for today. I'll see you in class.